Hayashi. I'm Yasunori Kamiya, so from Preferred Networks. So let me tell about my company. So the Preferred Networks from the 2014. Yes, located in Tokyo, Japan, and we have a subsidiary company in California. So our goal is to create the IoT development using deep learning technology. So we also the focus in the automotive and the manufacturing and the bioscale field. Today's outline. So I'll introduce our company and our IPC system and the industrial products related to autonomous robotics, this field. So the result of IPC is that we got the second place at big task and the first place at the slow task. We use the two Fanuc robot arms and the two types of hands and two types of image sensors that are mounted at the tips of the arm. So the system uses the vacuum and memory, and so the first and scanning by the image sensor. After that, using the vacuum hand to pick the item. So for the some specific items, so we use also the gripper hand. In this case, the system picking the meshed pen cup. So also our system consists of the robot arms and the vacuum system and the sound controllers and the sensors. So the most of the units are connected by the several interface, USB and Modbus. Also, we use the two types of image sensors, real sense and FX82 to interpret the weakness of each sensors. So real sense has good accuracy, but it is unable to capture the depth image for the black and the metallic, so the transparent object. On the other hand, the FX8 can capture the several level of the depth image from the objects.
So that's a laser sensor?
Yes, and it is the kind of laser. This is the vacuum hand. So the vacuum hand can move the item from the one place to another place by using the vacuum system and the barrels, the suction cup. So which can change the angle by the linear servo and the metal rod. So also this is the gripper hand to grip the item between the metal blade. Also to open close the blade, the screw and the fraction, the rotational servo used. So yeah, here the real sense and the FX8 mounted and the connecting to the robot here. So this is the vacuum system. We use the industrial grade vacuum cleaner. So we choose this vacuum cleaner, but we have two opportunities. So to candidate the vacuum cleaner and the pump, but we choose this one because the amount of the air is very important. So if the some space between the item and the barrels, so especially for the items with the non-flat surface, so in that case, the amount of air is very important. So, and the exhaust valve is used to release the item quickly to remove the negative pressure.
Have you done something about the noise since?
No. Just the vacuum pump. Yeah, so and this is the subsystem, and we will choose the include the product. So the quick delivery, the original, and the cost, and robust. The linear start is for the changing the angle of the vacuum pump, and the tips of the vacuum pump, and the original start is for the gripper. So we also use the Arduino. This the system consists of the AWL microprocessor and the simple IDE, and we just use Arduino to read the value of the sensor and to control the actuator. Therefore, the vacuum system, the pressure sensor, exhaust valve, and turn on/off for the vacuum cleaner, and also the shelf calibration. We explain it in next slide, and then at the distances. Here I talk about the beam coordinates and shelf calibration. So there are the two motivations for this. So the first one is the dealing with the rule, and the shelf is with the moved by the APC's organization members within the 3-6 meter areas. So and the team members must not measure the moving shelf position by hand. And the next motivation is that we want to program the arm motion in a way we can repeat it for the all beams. So beam coordinates are described by the beam name and the left position. Left position. Vertical original coordinates or origin coordinates. So this can separate the difference between the beams and the motion programming, and also the separate between the shape movement and motion programming. So the first, the system calibrates the shape position, then the motion control unit, and then the robot arms position by using the beam name plus and varying the beam coordinates. Then the converter converted the varying wires coordinates. So robot arms can only understand the varying wire coordinates. So the shelf here about the shelf calibration. So the holding the shelf between the two arms, the top view, and detecting the shelf corners by the distance sensor here on the side and tips of the arm. And during scanning back and forth, defining the point at which the sensor value differed, the sensor value differed with the other position significantly as a corner. So it's about the item recognition process. The real sense and FX capture the color image and the depth image. Then the color image is segmented by using CNN, deep learning. So after that, analyzing the item about the estimate the vacuumable point using also the CNN, very similar way for the segmentation, and estimating the normal direction of each point. So and the item pose and the direction for the grip hand. So and anyway, so And the other important thing is the converting the coordinates. So we use the four types of coordinates: color image, depth image, and world coordinates, and also beam coordinates. So we have to convert its coordinates. So, and the arm motion programming. So the reprogramming the arm motion in each beam using beam coordinates described in the previous slide. So for example, the vacuum hand. So we control the arms and the angle of the tip hand and the vacuum system. So the controlling arms based on the estimated vacuumable point by using the tip line and a normal direction. So by matching the normal direction and the direction of the vacuum surface of the hand below the surface up direction. And also the gripper hands. So we control the arm and the grippers. And so control the arm based on the estimated item direction. So and the longitude direction and the grippers. So that we match the direction to control the grippers for the matching the direction. So here is about the general planning. So the item movement. For picking tasks, we have two types of movement. So direct picking and beam to beam movement. So beam to beam movement means for example the situation in front of the target there's a non-target object exists, so we have to remove that non-target object and move it to the other beams. So and for the storing task, just direct storing to the beam. So the three types of the program or something. So for example for the direct picking, we have to calculate which item is the fast picking. So and which being the destination beam, and the direct story, which being the better to get the highest score. So for that, we consider the degree of the difficulty and the score. So here the difficulty is about the calculated based on the number of the non-target item in the beam. It means the crowded beam or not. The system that decided the target item on the target beam using this difficulty is 100 times take underscore. Yeah, this is the actual algorithm, but I passed. And if you know the previous question, please ask me. So this is software overview. So so we use rows to control the whole system. So there are many nodes, and these nodes are collected by the topic, service, and action. This is the last choice. So the remaining challenge is the sum challenge. The first is so we face some trouble and unstable of the hardware, such as the sensor and robots, and also the writing condition for the targeting sensor. But this problem is the very common problem for the robotics competition. So we had some the experience about the robot competition. So yeah, from the so the singularity of the robot. So the robot motion are limited by the singularity. So we avoid it by the effort of the motion construction. Yeah, but in other things, for example, the depth, and yeah, so by adding the extra axis, so the similarity has been avoided. I think we need more accuracy for the estimation. And for the situation that some items are collected and included, and for example, in the thought, so we need, I think that need more accuracy to estimate the item pose and the item boundaries. Yeah, because our system mistook the missed item. So and also for the small item, small items, and the for accurate handling. So especially the vacuum hand. So very difficult for example, the toothbrush and the scissors. So I think it's very not very, but really hard to pick for my. So adjusting the real situation. Yeah. So this is in the real challenge. So the vacuum hands the try to pick the item. So actually that is the bunny book. So we never miss the practice in my company's environment. Yeah, so I think the reason would be the difference of item condition. So in the real challenging one is the new one, but in the practice there is the used one. So probably the surface condition is different, I think. And next thing about
excuse me, just regarding in practice the difference there. Was the gripping position the same as in the practice during the real challenge?
Yes, I think so. But yeah, so all of the case in the practice in my company. So the system never missed to pick. Yeah, this is just first time to the failed against the big, the bunny books. So if the pick the bunny item, so we would be the winner. Yeah. Anyway, so for the industrial products, the partners and integrated picking robots and the China. So our company collaborates with many industrial companies, such as the Fanuc and Toyota automotive company. So with Fanuc makes robotics frameworks for IoT, and with Toyota we also research about the IoT for automotive. So by the relationship with the Fanuc, we use the Fanuc lockdown for ABC. Also, this is one of the applications in our company. So, in intelligent beam picking robots. So, this system can run how to pick the item automatically in 8 hours. So, I show the movie. So this robot automatically learns how to pick the beans. So the robot can recognize the picking is successful or not. Then running by the result. Running the how to pick the item by the model deep learning. So the red point is the calculated pickable point. So the first situation, the success rate is only the 6%, but after 8 hours, the success rate became 90% without any human tuning.
If you run even more, is it going to get to 99% or 100%?
No, this is, I think that probably around the saturated success rate.
So the successful rate can it go not more than 90% if you practice more?
I think that there are other difficulties with that picking task. So the 90% is the limit of the. The 90% is also the very similar with the human tuning level. So I think it's a limitation of the success rate.
Did you try other parts and other type of gripping?
No. So we only try to do this type of gripping. Yeah.
I have a question. By human picker, do you mean a human picker to pick the item by hand, or it trains a robot or program a robot to pick?
No. So the human train or the programming the picking the task of the motion. Yeah, so that's me. So the next is the chainer, the top-up. This is the famous product in our company. This is the open source deep learning framework. So of course we use this framework for the most of all of the product using deep learning, including the FBC system. So the many researchers and developers can use this framework to build this safety on the product. So this is the comparison with the other framework. So and anyways, the China feature is about the dynamic network construction. It means we can change the network construction in the runtime. So and also for the RNN, China has much less limitation compared to with the other frameworks. So we could say that China is the best framework for that one. Thank you.
The framework, does it include the work for the APC sample?
So the APC system is constructed by using the China. But so probably the APC system is released by the open source. Yeah.
There is a question.
Yes.
Did you use this framework to get the picking point for APC, or you did not do that?
So you mean the result of this?
Yeah.
No. So this is no. We just trained by the data set the human. How can I say the labeling or something.
So the deep learning that you emphasize is mainly for identification, object classification, and
Yes. This technique is very similar with the segmentation. So the input image and the how can I say the point the human the choose the choose
The normal.
Yeah.
So the neural network learns the classification and the normal vector of the surface.
normal direction is calculated by the other programs. Yeah. So just output these orange points. Yeah.
So what's the training set for segmentation, for example, here? What the data that you generate to train the network?
Yeah, so just calculate the human labeling, so annotation. Yeah.
So you're placing the specific case, you place different objects in the bin, take images, annotate by hand, and generate the training set? Is something like that?
You mean do we use some generation technique?
Yeah, right. What's the generation technique?
Yes, okay, so anyway, so I will explain about the first type, the first way we use the CZ data for the pre-training. After that, we use the human annotated data to
So for the orange point, what is labeled the human click that? What is it? Okay.
Okay, I think that's
One more question, sorry, just one more. Calibrating the shelf. Why not using the camera, another extra sensor use the distance sensor?
Yeah, because the accuracy of this camera.
Okay.
Yeah, so
Yes.
this sensor is the more accurate than because this yes, that's it.
Were those two manipulators on separate controllers, or was it one CPU running both arms?
They're actually one CPU. So, but we use the two laptops because of the performance of the laptop. Yeah, but the controller. So if you need the controller of the robot arm, so the separated controller, maybe this, but they connected to the lamp by fiber and one laptop. Yeah, but we use two or three laptops for the because of the performance of the laptop. So for the deep learning and the other calculation for the application.
Thanks, Yasunori again.